so we're back talking about section 6.7. I'm doing some sample problems from your homework. So if you look with me, I'm on number 13. I've got a sample number 13 up for you, and I've also added these in as a document in your Blackboard shell if you want to look there or print those off. All right, so we've got number 13. We switch gears to solving the system by addition. Sometimes addition is called the elimination method. So what we try to do in the addition method is add the two equations, and you do have two equations. If you want to consider that equation 1 and this is equation 2, we're going to add these equations together such that either the x's cancel out or the y's cancel out. So on this one, number 13 is where they switch into this method. It is already set up perfectly for this method. You see how y and negative y, if I added these like this was an addition problem, it just naturally cancels out. Now that's not always just automatically set up that way, but this one is. So we can add straight down for our x's. We have 1x and 2x, which makes 3x. The y and the minus y cancels out. And then 5 plus 1, they're both positive, so 6. That gives us a solvable equation. We can divide both sides by the 3, and we get x is 2. Now you might remember in 6.7, it's solving systems of equations. So you're looking for the solution that works for both equations. So it will be a point, an x and a y coordinate. The point is, if you were graphing them, it would be the point where if you graph a line, graph the other line, they cross each other, the point of intersection. That's the common point for these two. So it says x is 2, but we need its y value. You can get the y by solving x is 2 in for this x or this x and solving either one of those equations. So I usually try to figure out which one looks easiest to solve. This first one looks just fine. It says x plus y equals 5. Once you know x is 2, it's saying 2 plus what is 5, basically. And we know that has to be 3. But doing our little technique with minus 2 and 5 minus 2 is 3. And there's how we know. The solution is the point. X is 2, y is 3. 0.23. You can see that works for both equations. 2 plus 3 is 5. And 2 times x is 2, right? 2 times 2 is 4. Minus y being 3, 4 minus 3 is 1. That is the one unique solution that works for both of those with the addition method. All right, so moving on to number 14. Number 14 also requests that we use the addition method, but you know, in actuality, you use any method you like. We have 3 methods to choose from and get that right answer, and we're all happy. So if you prefer substitution method or graphing, by all means do that. If I'm going to use the addition method on number 14, it's not going to naturally work for me. 5 and minus 2 leaves 3 x's, and negative y would be negative 2y. So nothing naturally cancels out when I add these two. You know, we're trying to add these lines so that either x cancels or y cancels if I'm going to be able to solve it. So it doesn't naturally work, but I can manipulate one of the equations, and we do have equation 1, equation 2. So you can manipulate these equations to make these be opposites. Like, for example, equation 2, I could take a negative 1 and multiply it across, or just change all the signs, and then it's going to be a positive 1. Now again, you have to, whatever you do to an equation, you have to do it to all parts, or both sides. And in this case, multiplication of both sides by negative 1 will distribute the negative 1 and result in a positive 2x, a positive y, and make that a negative 6. Just basically changing all of its signs. It's still absolutely equivalent to equation 2. It just looks a little different, but absolutely the same equivalent equation. Now if I take equation 1, 5x minus y equals negative 15, and I add those two equations together, it will work for me like the last example. A negative y and a positive y will cancel out the y's. I need something to cancel. I could have worked on the x's, but it would have been a little harder there. 5x and 2x adds to be 7x, and the y's are canceled. Negative 15 and minus 6 is negative 21. Now I have a solvable equation that I can divide by 7. 7 divided by 7 makes just 1x. Do the same thing to this side, divide by 7. Negative 21 divided by 7 is negative 3. There's one of my solutions I need. You know, I need an x and a y, a coordinate that solves both of these equations. Okay, so now that I've got x equals -3, I need its y counterpart, and I can go to any of these former equations and do that. Whichever one you think looks easiest to you, in any of its forms, you'll get the same answer regardless. So I'm just going to pick, let's see, I've got this 2x plus y equals -6 right here. So I'm going to plug in this solution, -3, where the x value is. So 2 times -3 plus what equals -6. And you might just already think about that. That would be -6 plus what equals -6. And so we know y is going to have to be 0 for that to work. But going through our process, we would take our -6 across the line, makes it +6, and there you see 0. So y equals, and it is a positive y, or regular y, is -6 plus 6, y equals 0. And that 0 is a number, you know, so don't discount that and say, oh, no solution. No, y equals 0 is an actual answer. So that is our solution. X is -3, y is 0, is the point of intersection, or the common point for those two lines. We could check that out back in the original problem. Make sure both of those, that point works in both of those former equations. So 5 times -3 minus 0 should equal -15. And you check that out. That's -15 minus 0 is -15. That is true. Check it in the second one. -2 times x is -3 minus y is 0 should equal 6. Calculate that. That'd be 6 minus 0 equals 6. Also checks out. So that confirms our answer. All right, let's look at number 15. Okay, we have a new set of equations. It requests that we solve it by addition, but like I said before, you solve it with substitution or graphing, whichever method that you prefer. Just get to that answer. So I'm going to solve by addition, though, just to demonstrate that again. If I added it in the form it is now, nothing would cancel out, and I wouldn't be able to be productive and get the answer. I would get 5 x's, you know, there's a 1x there, so that would be 5 x's minus 1y, and 4y would be 3y. So I wouldn't get anything to cancel out naturally, so we have a little more algebra to do. We have to manipulate our equations so that either the x's will cancel or the y's will cancel, and that's totally per your design. It works either way. I'm going to label this equation 1, this one equation 2. I'm going to choose to multiply equation 1 times 4. Can you see if I multiply this by 4, and I have to do it across all terms, distribute it, it'll make 16x, and then that 4 will make that 4 times -1 or -4y, so that when I add, the positive 4y would cancel. So that will be productive for me. And I'm allowed to do that, right? I can times all those terms by a positive 4 and make an equivalent equation. Just every term by 4. So now this is my new equation 1. It's equivalent, just bigger numbers proportionally. Then I can add that to equation 2. I didn't have to do anything to equation 2. It just worked out nicely there. Now when I add 16x and 1x is 17x, minus 4y and plus 4y, that's what I wanted to happen, something to cancel. 12 and 22 is 34. Now this is solvable by dividing by 17 on each side. We can get x, or 1x or x equals 2. X equals 2 is the x part of our solution. We need to find its y counterpart. In any of the former equations, you can do that, plugging in x is 2 here, 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 or here, gives you exactly the same answer. I think I like equation 2, looks like maybe the easiest one. So I'm going to take 1x, which now is x is 2, plus 4 times y equals 22, and solve that for y to find the second part of my answer. So I'll move the 2 across the line, giving me 4y equals 20. Divide by the 4, and y will equal 20 divided by 4, or 5. So our solution is x is 2, y is 5. Write that as a 0.25. That should be what works for both of those. Okay. The last two, I think it's the last two. Yeah, the last two are our special cases, clear, when we do our process, something funny happens. You don't just get a 1x equal, the x will disappear. You'll lose your x or your y, you'll have 0 of your variable. And that means something special. Either the equations were, the lines were parallel, so they never crossed. You know, if there's a false statement when you do this, you lose your variables and there's a false solution left, then that means they were parallel or inconsistent and there's no solution. All right, let's see what happens here on number 16, for example. First of all, it's not really lined up in order of x's, y's, and constants, so you might need to clean it up. You know, I can't really tell these are parallel lines or if they're just the same line because they're not really in the right ordering. So consider this equation 1, equation 2. This one, you know, it's all out of order. I want my x in front. This 4y should be over here, so bring 4y over, makes it minus 4y. And then my constant should be on the end. So the minus 32 crosses over, becomes positive 32. There it is in a cleaner standard form. Equation 2, likewise kind of messed up. The 5x is on the left, but scooted over a little bit, so it'll be lined up. And then this y needs to cross over, become minus y. And then the 8's already on the right side. So now they're cleaner. I might be able to really tell if I times this by 4, you know, this is going to be exactly that. Do you see if I times this equation by 4, that'll be 20. That'll make that a 4. And it'll make that 32. These are really just the same old line. And if we graphed it, we could use our graphing method. I don't know exactly how it looks when graphed, but however it looks, say it's this line. So I graph that line, and then I graph the other line, it's going to lie right on top of it. They're really just the same line, a line on top of a line, which means they're dependent lines, and there'll be infinite solutions. Why infinite, you might say? And that's because the solutions where they cross, if they're lying on top of one another, they're crossing all over that line, right, in infinite points along the line. So infinite solutions when they're just the same line. But let me continue on. Say I don't recognize that this is just that times 4, and I do the algebra steps. I would either try to get the x's to cancel or try to get the y's to cancel. It doesn't matter. But let's say I focus on the x's this time. And I say, I wish that was a negative 20. So then 20 and a negative 20 would make the x's cancel. Well, I can do that by multiplying everything by negative 4. So if I distribute a negative 4, it makes that negative 20x. The negative times negative makes that plus 4y. And negative 4 times 8 is negative 32. So that is equivalent. You know, we can do that as long as we do it all the way across to every term. Then when I add that other equation, look what happens. 20x minus 20x is just 0. You can put 0 if you want. Negative 4y and positive 4y is 0. And then 32 and minus 32 is 0. So you just have a big 0 on one side. There's no variable left to solve for. It's just a true statement. When you wind up at the end of this process with a true statement, that means they were the same line, a line on top of a line. Again, that goes with dependent and infinite solutions. Now, number 17, you're going to see maybe the other. I'm not positive without working it. We're going to run out of time on this video segment. But on the other problem, if this would have been 0 equals 3 or any false statement, if you get a false statement, it means they're parallel lines. So that's the other possibility. A false statement, again, means parallel lines, which means it's inconsistent with no solution. So you'll want to put those down in your notes, that those are the wordings that go together. You know, most of the problems that we work on section 6.7, you will have one solution. That's a consistent solution. That's what we expect most of the time is going to happen, that the equations run into each other and cross in that one point, the solution. But then there's these special cases. What if they don't? If they're parallel, no solution. And if they're the same line, there's infinite solution. All right, I hope that helps.